Hi, my name's Andrea Loyan.
And I'm Chandler Jardin.
We are from the Mechanical Engineering Department of the University of Massachusetts Dartmouth, and we did our research on the stability analysis of an offshore vertical access wind turbine platform.
The reason for conducting our study is due to the increased attention regarding fluid-structure interaction problems that are experienced between the floating platform and its surrounding fluid environment. Now, while platforms already exist for horizontal axis wind turbines and are commercialized, platforms for vertical axis wind turbines are still under research and development. Our study is going to focus on the stability of the platform, as that is one of the primary reasons as to why offshore platforms aren't widely used for vertical axis wind turbines. To go along with our study, we have selected the Getz 30 kilowatt vertical axis wind turbine to use for our platform, which can be seen on the right. Here we have a chart that is depicting the exponential growth of the estimated offshore wind capacity around the world that is based on developer-announced commercial operation dates through the year 2025. At the current year 2021, you can see we are about 37,000 megawatts of installed capacity. If you look ahead to the year 2025, you can see that number triple in growth as we expect that installed capacity to increase to almost 120,000 megawatts. This data was collected around the world and was provided to us by the National Renewable Energy Laboratory and the U.S. Department of Energy. Our objective is to design a semi-submersible platform that will be used for floating offshore vertical axis wind turbines. We will be making a scaled-down prototype that is 3D printed, and we will be studying the stability and the dynamic response of our prototype. This is going to be achieved by studying the flow-induced motion response of the platform over a wide range of flow velocities at various angles of attack.
Here is a table of our product design specification. Listed are our top 10 needs for our platform, and in the rightmost column is their importance to us and our customer. The importances ranged from 1 to 5, with 5 being the most important and 1 the least. This matrix was helpful to keep in the back of our minds, so further down in our project we could reference it and make sure we were keeping our priorities in order and addressing all of our needs. For our scaling method, we utilized fraud scaling. You can see the different relations the different variables have with the scaling. After multiple iterations of our platform and taking into consideration our testing environment, we concluded that a fraud scaling value of 35 worked best for our experiments. In the other tables, you can see scaled down values of the platform, along with the wind and current turbine that we plan to utilize in further experiments. The final two tables in the right-hand corner are the values used for the environmental conditions. The ranges were found by taking the most placid days and going all the way to the most extreme conditions, which have ever been recorded. For this experiment, we only focused on the current range. This range was given to us by Dr. Cowles, who gave us a range from a nor'eastern up in Maine from 2010. This nor'eastern had 1.8 meter per second currents, and we rounded up to get the most extreme case.
Our design process began by performing research on existing floating offshore platforms. Once enough material was gathered, we began making designs of the platform in SolidWorks. We would make subtle changes as we performed calculations based on buoyancy, weight, and size until we reached a final design down below which would work for us. Once our final design was reached, we would manufacture our platform by 3D printing the platform in our own FSI Labs 3D printer. From here, minor touch-ups were added, such as spray painting the platform. That way it would be waterproof when we perform tests in our water tunnel.
The 35:1 scaled model of the semi-submersible platform prototype was flexibly mounted and placed in the test section of the water tunnel, using a 1 degree of freedom air-bearing setup that enabled the motion of the platform in the direction perpendicular to flow. In the bottom right-hand corner, you can see a picture of this water tunnel. The platform was attached to a U-bracket extension of 19 centimeters to hold the platform 2/3 submerged into the test section. 3 different angles of attack, 0 degrees, 90 degrees, and 180 degrees, with respect to incoming flow to the platform were tested. An image of this is shown in the upper right-hand corner, where you can clearly see each of the 3 degrees. Flow-induced motion response of the system was studied over a wide range of flow velocities and platform's angle of attack. The flow-induced motion amplitudes and frequencies were collected using a Panasonic HL-G1 series compact laser displacement sensor at each of the flow velocities. When a flexible or flexibly mounted structure is subjected in fluid flow, this body can be forced to oscillate due to the flow forces. This oscillation is called flow-induced vibration, or FIV. When a flexibly mounted circular cylinder is placed in fluid flow, vortices shed as the flow goes around the cylinder. The frequency of this vortex shedding can change by changing flow velocity. When the frequency of shedding locks in with the system's natural frequency, large amplitudes of oscillation occur. This occurrence can happen for relatively large range of flow velocities. This range, where the cylinder is subjected to vortex-induced vibration, or VIV, is known as the locked-in region. A decay test in the water yielded a natural frequency of 0.5833 Hz. Experimental runs were recorded over a 90-second duration at each flow velocity and angle of attack. The graphs show a dimensionless amplitude and frequency of oscillations versus a reduced velocity. Equations for all 3 of these can be seen in the lower right-hand corner of the slide. The graph also shows dimensionless amplitude of oscillations in the cross-flow direction versus the reduced velocity of all 3 angles of attack. It is observed that the platform experienced maximum amplitude of oscillation with 0 degrees angle of attack, which means that one column was upstream while the other 2 were downstream. The maximum value of the dimensionless amplitude was equal to 0.22, which implies that the platform is oscillating about a quarter of the column diameter at its maximum. The maximum oscillations occurred at an incident of 0 degrees because the vortex shedding is fully developed at all 3 columns due to the one upstream column having a weak wake disturbance and the 2 downstream columns. The lock-in range for the 0 degree was observed at the range of 7 to 11.67, which was the longest lock-in range of all 3 angles. At 90 and 180 degrees of incidence, similar to each other, the largest amplitude was equal to about 0.14 to 0.16. Although the amplitude was similar, the range where the oscillation occurred differed between the 2 angles of attack. The lock-in range for the 90 degrees was observed at a range between 7.44 to 12.3. This is the smallest range, but the oscillations persisted at higher reduced velocities. The lock-in range for 180 degrees was observed at a range of 6.33 to 11.2. Unlike the 90 degree incidence, the oscillation dies down at a higher reduced velocities. One notable difference is that the incident of 180 degrees compared to both 0 and 90 degrees has a lower reduced velocities. Oscillation has occurred. Overall, this experimental test has shown nominal amplitudes of 25% of the external diameter observed in the cross-flow direction. It was also concluded that motions are due to the presence of vortex shedding. At the end of our experiments, we were able to conclude that flow-induced vibrations can be observed over varying angles over a range of flow velocities. The lock-in ranges were observed to differ with the different angles of attack. Finally, through MATLAB, we were able to obtain the graphs to better see and understand the effects regarding flow visualization and vortex shedding patterns. Finally, this platform design will also be submitted to the Marine Energy Collegiate Competition, which will be held at the end of April.
We would like to thank Dr. Saeed Agazada for help with our studies, as well as the National Renewable Energy Laboratory for funding our research. You can learn more about our project at marineenergy101.wordpress.com or learn more about our FSI lab at fsilab.sites.umassd.edu. If you would like to contact me or Andrea for any further questions on our project, you can reach us at our email addresses down below.